everybody, my name's Jack Pearce. I work as a solutions architect for DigitalOcean and I'm based in the UK. So today I want to give you a quick demonstration on how to run NVIDIA NIMS on DigitalOcean Kubernetes. The documentation that I will link you to and reference you to, that was created by Bikram Gupta, who is our lead product manager. What infrastructure will we be using today? We'll be using Droplet, and we'll be using our DOKS, which is our managed Kubernetes, DigitalOcean Kubernetes. And what will we deploy? We'll be deploying a large language model, Meta Llama 3.1 in this instance. We'll be using NVIDIA NIM to deploy that. NVIDIA NIMs are microservices that accelerate the deployment of models on your infrastructure. We'll deploy some observability, so Grafana and Prometheus, which will allow us to see our GPU metrics. And we'll also talk about and deploy the NVIDIA GPU operator, which uses the operator framework within Kubernetes to automate management of all NVIDIA software components needed to provision a GPU. So it's a really important skill to learn if you're going to start working with GPUs on Kubernetes. Our observability will look like this once we're finished, and I will also link to the NVIDIA GPU operator documentation. Really good idea to just go in and have a quick read of that. The GitHub repository that we'll be using today, I'll also be linking to. That is from Bikram. So now let's get to the demo. The first step is to sign up at build.nvidia.com. If you use a business email address, you get an API key that allows you to self-host the NIM on your own infrastructure. And then once we've signed up and logged in, we can just select any model, go to Docker, and if we click on Get API Key, it will give us our Docker registry username and password. These are the two items that we'll need to use in our Kubernetes cluster in order to be able to download the models and the container images. The next step is to browse to the DigitalOcean control panel, go to Settings, and then click on Feature Preview. And in here, you'll see all of our active betas that you can enable on your account. So you just want to enable GPU droplets if you haven't already. And then for the next step, we want to create a DigitalOcean Kubernetes cluster with a GPU worker node. So for all of the commands that I'll use in this video, I'll just be copying and pasting them. If there's anything, just to save time, if there's anything that I think I need to call out, I will run through that with you. So to create a Kubernetes cluster, we're going to use the doctl DigitalOcean command line tool. And in this, we're just saying Kubernetes cluster create. The name of the cluster is GPU cluster. The region is Tor1. So for a list of regions, you can either get that from the doctl tool, or if you browse to our documentation, click on platform, click on regional availability, you can get a list of all our regions and data centers here. So we could do a doctl Kubernetes options regions, and then we could then do the same thing for versions. That will return us a list of versions that are available to deploy. We're also telling it to create a node pool with the name GPU worker pool. And this is our NVIDIA H100 GPU worker node with a count of 3. If you check our documentation, you can see the available sizes. You may also want to deploy NVIDIA H100 by 8. That's 8 available GPU. The other thing I could do is I could just add a GPU worker node to an existing cluster. In this example, I'm saying add a node pool, create a node pool on my cluster that is called GPU cluster, H100 times 1, 4 of those. For this demo, I'll be deploying one GPU droplet and NVIDIA H100. That's sufficient to run the Llama 3.1 8B model. Once we've run our command, we'll come into our control panel and click on Kubernetes. And we can see our Kubernetes cluster here that I created. We'll copy this command. This will save our kubeconfig to our local machine and switch our context to that cluster. Just want to take a quick look at our worker nodes here. So we can see our new node here, GPU worker pool 1. And if we come into the user interface, click on resources, we can also see our new GPU worker node here as well. And it's a H100 by 1. So what I want to do is just take a look at the labels that we apply to these worker nodes. So you can see that we apply a number of DigitalOcean labels to our Kubernetes worker nodes anyway. But for these new GPU worker nodes, we've got these additional labels: GPU brand Nvidia, GPU model H100. We've also got this taint as well, nvidia.com GPU no schedule. So the reason for this is that you can use these labels and taints in your workloads to schedule pods that match these particular labels and taints, because you might not want your regular workloads going onto these GPU nodes. So let's git clone the repository that I was talking about earlier. The first thing we're going to do is verify the GPUs on our worker nodes. So if you've worked with GPUs before, you'll be familiar with the command NVIDIA SMI. We're just going to deploy a daemon set that runs on all the worker nodes so that we can easily run that command. So you'll see in this directory, we've got this CUDA bash, and this is a daemon set. So let's just take a quick look at this file and see what it does. So this is a CUDA runtime daemon set, and you'll see that in the specification we have node selector docs.digitalocean.com GPU brand Nvidia, and we've also got our toleration down here, because if you remember, we have a taint on the GPU worker nodes. So what this does is this deploys the Nvidia CUDA runtime container image. It prints out the result of the command NVIDIA SMI-L, and then it exits the container. So we're just going to apply that and run that across all of our worker nodes. The container image that's being pulled down is a few gigabytes, so it may just take a few seconds, and then we can check the logs of that daemon set, and we can see our NVIDIA H100 GPU here, which is great. And we could also just run it on demand. We can exec into the container and run NVIDIA SMI-L and get the same, and get our UUID of our GPU if we needed it. In the next step, we'll set up some observability. This is optional, but I do recommend it. So we are going to install metric server on our Kubernetes cluster and a Prometheus stack. So we provide the commands just to make things easier for you. You could also just run these Helm commands manually. So here we've got the metric server install, we've got the Prometheus install, and these are the values that we'll be using. We're just giving it some additional config in order to be able to scrape some GPU metrics from our GPU nodes. There's also a password here that you want to change for Grafana. Let's go into folder number 2 and run our first script, and our metric server has been installed. We can rerun that same script to perform a Helm upgrade of that particular component. Let's do the same thing for the Prometheus stack. And again, the Prometheus stack has just been customized to use persistent storage. So it'll attach a DigitalOcean block storage volume to your Kubernetes cluster. And it also includes some additional configuration to scrape the GPU metrics. And again, these shell scripts are just running Helm install. So both of those are now installed. And if we do a get for our pods in all namespaces, we'll see we've got this Prometheus stack namespace, and we've got the Prometheus stack up and running. So next thing we can do is just do a quick port forward on port 3000. Open up a web browser, browse to localhost 3000, log in with the username of admin and the password that was set in our manifest earlier. If you remember, I said to change that. And you'll come in here and you can see various Kubernetes dashboards. But what we'll do is we'll come here in our next step and we'll import a dashboard specific to the GPUs that are installed on our worker nodes. So for the next step, we want to deploy the NVIDIA GPU operator. Let's go into folder 3. And in folder 3, we've got the GPU operator install script. Again, it's just a Helm command that will install the NVIDIA GPU operator. Now, when we talk about the GPU operator, it's helpful to understand what it is and how it works. There is a link in the Git repository to this page, and it explains what the GPU operator does and how it works. Essentially, it's a component for NVIDIA Kubernetes GPU management. It includes things like drivers, container toolkits, Kubernetes device plugin, node feature discovery, GPU feature discovery, MIG manager, and DCGM. It's open sourced and it's maintained on GitHub. It's essentially everything that you would need to get up and running with NVIDIA GPUs on Kubernetes, and the documentation is excellent. In our example, what we're going to do is we're going to deploy the operator with these values. Now, you'll notice we've got things like driver enabled set to false. The reason for this is that DigitalOcean GPU worker nodes come with the drivers required to enable GPU support. So we can see here in our DigitalOcean documentation, it says that we install and manage the drivers required to enable GPU support. You can see that in our changelog here. So we install the CUDA driver versions 5509007. However, GPU discovery, health checks, and configuration of GPU enabled containers, you need additional components. So that is what we are going to install now. There's also a call out here for monitoring your cluster using Prometheus. You need to install the NVIDIA DCGM exporter. Now, if we come into our operator value, we can see that we are installing that now, and we're also installing the exporter as well. Let's go ahead and install the operator. So that ran successfully. We've now deployed the NVIDIA GPU operator, and let's just check the GPU operator namespace. We can see that our various containers are up and running. So the number of containers that you see here will depend on what values you've set in your Helm chart for what values you've set when deploying using Helm. So we've enabled things like DCGM and DCGM exporter, which I've just explained, and we can see those running here. So we've got DCGM exporter, DCGM, node feature discovery. So now we've got our exporter up and running, we can go back to, we can port forward again, reopen our port forward to our Prometheus stack to Grafana, and let's import a dashboard. So we'll come to dashboards and click on import. We just need to import this ID. So it's 12239. And that's the NVIDIA DCGM exporter dashboard. And we'll just select Prometheus as our data source. And now we've instantly got dashboards for our GPU. So it'll show you things like our GPU temperature, our power usage, our clocks, our utilization, frame buffer, memory usage. So it's really quick and easy way of just getting our GPUs into a dashboard. The next thing that we're going to do is we're going to set up some shared SMB storage. The reason for this is that if you end up with a multi-node GPU deployment, you need some kind of shared storage infrastructure that the nodes can access so that they can store and retrieve the models. And for this, we're just going to set up a droplet with SMB. So if we come out and we go into our folder number 4. So the first thing I'm going to do is I'm going to install CSI driver for SMB. You'll see that it creates a secret in our cluster. This is for the SMB username and password. Just be sure to come in and set this to something secure. And whilst that installs, what we need to do is we need to come in and create a new droplet in the same VPC as our Kubernetes cluster, because we want them to communicate over the private network. What we'll do is we'll browse to droplets and we'll find our GPU droplet, which is here. And if we click on networking, we can see which VPC that we put this into. So I put it into a VPC network called default-tour1. So that's where we want to create our droplet. So let's go to create droplet in Toronto, and we're just going to use an Ubuntu droplet, low specification. The $6 droplet is absolutely fine. We just want to make sure that it's in our default Tour1 VPC, which it is. And just remember that if we're applying a firewall to that SMB droplet, which I would recommend, we'll just need to make sure that we have a firewall that allows inbound access from our Kubernetes workers. So I'm just using the tag K8 workers here. That would allow all Kubernetes workers. If you just want to allow specific Kubernetes workers, so in this instance, I just want to allow this particular cluster to have access, what I can do is I can come into here and I can take a look at which tags. So this is a unique ID for this Kubernetes cluster. So I could just take that unique ID and apply that as a tag to my firewall when I'm defining my inbound rules. I could also lock it down to just SMB TCP ports as well, but just to make things easier, I'm just going to leave it like this. So I've got my DOKS SMB droplet here, and I just want to come into my firewalls and just apply my K8 worker firewall to this droplet as well. So I'm SSH'd into that droplet, and I'm just going to git clone the repository, and then I'm just going to apply the Samba server on droplet scripts, which you can inspect, and it will just go ahead and install a Samba server. One thing to note, actually, one thing that we do need to do, we need to create a volume on this droplet. So when we download Llama 3.1, for example, it's going to be about 8 gigabytes. If we download the 70B model, it's going to be about 40 gigabytes, somewhere around there. So you want a volume that's large enough to store the models that you intend to use. And we want to make sure that the volume is mapped to the same place that this script is referencing. If it doesn't, we can just modify the script so that it references the correct place. So let's go back to our droplet and go to volumes. I'm going to click on add volume. I'm going to add a volume that's 500 gigabytes in size, and then we want it to automatically format and mount. So we'll click on create volume. And then if we run a df-h, we can see that this volume has been attached and it's here. It's at volume tour01, tour102. So what I want to do is I want to browse to my folder, and then I just want to do a replace for this and just replace it with our correct volume path, and then we can run that script on the server. That'll now go ahead and install Samba server and mount and export our new volume as something that can be mounted by the Kubernetes cluster. Remember as well to come in here and modify the SMB user and password that you set earlier when you created your Kubernetes secret. So once the script is finished running, we'll browse to our volume mount and we'll see a share folder. So let's go back to our Kubernetes cluster, and in this directory we've also got an SMB test. This SMB test will create a persistent volume claim, and it will create 2 pods, and it will just write a file to that SMB persistent volume claim. So one thing that I forgot to do there was set the correct IP address of the SMB server. So in our example, we've got 10.118.0.8, and I'm actually running mine on .2. So what I'm going to do is I'm just going to come in and run a delete on my SMB test. That'll delete the persistent volume claim and the pods that were created. I'm going to delete my storage class as well, and then set this to the correct IP, which is 2, and reapply it. So now our storage class is set to the correct IP of our SMB server that we created earlier. And now we can go in and reapply our SMB test. And then let's check the logs for our SMB controller. And we can see here that it successfully provisioned a PVC. And we can see here that it's created the PVC again, and it's bound. So let's go into our SMB server and browse to our volume and then our share folder. And if we do a list on that share, we can see the PVC has been created here. So that's excellent. So that is our Samba server up and running. If we go to exec into our various pods, we can see that our test file has been created. And if we go into this PVC folder, we can again see those test files. So everything is working as expected. We've got multiple pods here that have access to the same storage with a read write many. Okay, so now we're at the exciting stage where we're going to actually deploy our large language model. Let's go into folder number 5, and in this folder we've got a number of different examples of how to deploy Llama 3.1, which is a large language model. We're going to use this example here, so let's just take a quick look at this manifest. So we're going to pull down this Llama 3.1 NVIDIA NIM image. We are using this registry secret, which I'll give you an example in a minute. We use our SMB storage class to store and download the model. I'm going to create that at 50 gigabytes in size. And you'll see down the bottom here, we're just setting our resource limits to 1 GPU. That's because in this demo, I've deployed H100 in a ×1 configuration. If we were deploying the 70B model, we would need to set our limits a bit higher. So you need something more, you need access to 4 GPUs for that. So first we need to create our Kubernetes registry secret that will be used to pull down the NIM container images from NVIDIA. In order to do that, let's go back to the NVIDIA build website, and we'll click on a random model. It doesn't really matter which one, and come over here to the Docker tab, and we'll click on get API key. That generates us an API key that we will then use to log in. So I've just exported that API key as a variable, and now we're going to do a Docker login to the NVCR container registry. If we go back here, we can see the username needs to be this value here. It's a little bit confusing because I thought that this was a variable that I was meant to be setting, and I couldn't find the variable, but it's not. You just type that, and then for the password we'll do our API key that we just generated. We get login succeeded, so that's excellent. And then what we want to do is we create a namespace on our Kubernetes cluster called NIM, and we will create a secret for the Docker registry, a Docker registry secret. We can see here that I'm just creating a secret of type Docker registry, which is called registry secret, the server, which is the NVIDIA container registry, the username, and the password, which I've already exported as a variable. And then we'll also create a generic secret called ngc API, which is our API key. This just allows our Kubernetes cluster to authenticate with NVIDIA's container registry. Next thing we want to do is just move up to the root of the directory of the Git repo that we cloned. And then we can take a look in the Helm directory, and in here we've got our Helm chart, which will help us to deploy our NVIDIA NIMS for large language models. There are a number of files and templates in here. You can dive into here. We're not going to do that for the purposes of this video. We're just going to deploy the Llama 3.1 8B model. So we just need to make sure that we're in the Helm directory, and then we can construct our command like this. So we're going to install it to the NIM namespace from the NIM LLM folder. The values that we want to pass it are from our folder number 5, this custom values SMB, which is the manifest that we took a look at earlier. So we'll hit enter on that, and what that will do is that will go ahead and start to pull down that container image, and then the container itself will start to pull down the model to our SMB storage that we just deployed. Let's take a look at our pods in our NIM namespace, and we can see here the container is creating. So let's do a describe and actually take a look and see what's happening. It's currently pulling down the Llama 3.1 8B instruct container image. It is quite a large image, so it may take a few seconds just to do that. If we take a look at our PVCs in our NIM namespace, we can see we've now got this 50 gigabyte PVC here, F234. So if we go back to our SMB droplet, we can see that has been created. So that's where the container image will download and store the model. So we can then map that same PVC to other GPU worker nodes, and it will have access to the same model without having to pull it down each time. So we can see that's now up and running. It's successfully downloaded the image. So now let's take a look at the logs for this container image. So we can see here that it started downloading the model. So it says this step might download additional files to run the model. In my experience, this takes anywhere from a few minutes, 10 minutes. It has to download the model, which in this instance, it will be quite quick because it's only about an 8 gigabyte model. Sometimes the models can be a lot larger, like 40, 50, 80 gigabytes in size, depending on which size you want to run. It has to download the model and then load that model, read it again from the disk and load it into memory. So it can take a few minutes, sometimes 10, 15 minutes to do that. And then if we come into our PVC that was created earlier, and we can start looking around, and we'll see that it's started downloading the model. So if we go into here and go to our blobs folder, we'll start to see these large files start to appear. And if we take a look at some of the size of these files, you can see that they're quite large. Let's go back and check the logs again. So when we start to see things like application startup complete, and when we start to see health checks in the logs, we know that the model has been downloaded and loaded into memory. And then what we can do is we can run built-in Helm test to verify that the model and the container is ready to take requests. So we'll just run this command here against the NIM namespace, and once it's finished, it will output some logs. Now, if we go back to our Grafana dashboard, we'll notice that as it loaded the model, the temperature of the GPU increased, which is what we'd expect to see, and the amount of power that the GPU is consuming also increased. But the most interesting thing probably is if we go down to our memory usage, we can see that our GPU has now got a memory usage as it's loaded the model. The GPU utilization is still very low. But these are just some interesting statistics that we can take a look at as we run our various workloads. Now, if we take a look at our NIM namespace, we can see that the pod that we created earlier is up and running. We've also got this service, my NIM LLM, and that service runs on port 8000, and that's how we can interact with our large language model. So we're just going to do a port forward here to that service on port 8000. We're just going to send a post request to it. You may have seen this kind of format before if you've worked with OpenAI API. And we're just going to ask it, what should I do for a 4-day vacation in Spain? And you can see that the model has replied. The other thing we can do to interact with our model is just use any OpenAI compatible tool. I'm just using a piece of software called Misty, M-S-T-Y, I think that's how it's pronounced. And it's just a great user interface, runs on Windows, runs on Mac. You can interface with any of the popular AI models. We can also set custom endpoint, which we're going to do now. So let's come in here and just set a remote API provider. We want OpenAI compatible, and our API endpoint will be localhost in this example. For API key, we can just enter anything we want. And you can see here we've got our Llama 3.1 8B model that it's detected. So let's give it a name, DOKS GPU. Click on add. So let's come in here and select model, and then we'll just ask it a question. Tell me about the NVIDIA H100 GPU. And we can see that our model is now responding. And because this is running on a H100, this is going to be super fast, super quick to respond. It's going to be able to handle really large context length, depending on the model that you're using. So we can come back into here and refresh this dashboard. We can just see that as we're using the model again, the power has gone up. We've now successfully deployed our large language model on an Nvidia H100 on DigitalOcean Kubernetes with GPU. There are some additional steps at the bottom of the GitHub repository that we won't cover in the video. That is in regards to running some performance testing. And we've also got some benchmark results for Llama 3.1 on a single node and multiple nodes as well. If you want to deploy Llama 3.1 70B on multiple nodes, there are some prerequisites, and they are all covered in the GitHub documentation with some additional examples. I just want to say thank you very much for watching this today. My name is Jack Pearce, I'm a solutions architect. Thank you to Bikram Gupta, our lead product manager, for creating the documentation. And if you have any questions, please feel free to reach out to me. Thank you and take care.